welcome to Mike Academy. So in this video, we are going to be considering this question to explain the concept of the principle of work and energy. The question says, a spring is used to stop a 60 kg package which is sliding on a rough horizontal surface as shown in figure 7. The spring has a constant K equals 20 kilonewtons per meter, which is held by cables such that it is initially compressed 120 millimeter. If the package has a velocity of 2.5 meters per second in the position shown and a maximum deflection of the spring is 40 millimeter, determine the coefficient of kinetic friction between the package and the surface. Okay, so this is the free body diagram of the system given to us. We have a spring, and from the question they said the maximum deflection of this spring is 40 millimeters. So maximum deflection of the spring was given simply as 40 millimeter. So let's pull out all the parameters given to us. Of course, we are given this package has a mass of 60 kg and it is moving with a speed of 2.5 meters per second. We are given initial compression of the spring. Initial compression, call that x1 to be 120 millimeter. So we convert this to meter, simply dividing 120 with 1000. That simply gives us 0.12 in meters. Okay, now they said if the package has a velocity of 2.5 meters per second in the position shown and a maximum deflection of the spring is 40 millimeter. So we have our final deflection or final compression. Okay, final compression x2 is simply going to now be 120 millimeter plus 40 millimeter. This gives us the final compression. So this simply implies that x2 is equal to 160 millimeter. So we divide this by 1000. That gives us 0.16 in meters. So this is our final compression. Not forgetting maximum deflection itself was given. Okay, maximum deflection, okay, call that delta x, was given simply as 40 millimeter. Okay, and 40 millimeter simply means 40 divides 1000, and that simply gives us 0.04 in meters. So that's our maximum deflection. Now, from the principle of work and energy, we have that T2 equals T1 plus U1 2. That's the principle of work and energy, where T2 is final kinetic energy, T1 is initial kinetic energy, U1 2 simply means the work done by the object. Okay, so let's pull the diagram and see. So we're given the initial velocity of this object. The object has a mass of 60 kg and a speed of 2.5 meters per second. So which means we can actually calculate the initial kinetic energy of this object. But since we're given a second speed, it simply means the final kinetic energy of this object is automatically 0. So with the mass 60 kg and speed 2.5, let's calculate initial kinetic energy. So initial kinetic energy, which is T1, is equal to 1 all over 2 mv1 squared, and this is equal to 1 all over 2, the mass is 60 times v1 is 2.5 all squared. So this simply implies T1 is equal to, so that gives us 187.5 joules. So this is our initial kinetic energy. But since V2 is equal to 0, this implies final kinetic energy T2 is equal to 0. So that means we found the first two parts of the work and energy principle. T2 is 0 and we have a value for T1. Now, what then is the work done? U1 to 2 simply means work done. Now, let's take a look at the diagram once more. We have a mass, and of course, this object is moving to the right. if it is moving to the right, again, this object is resting on a rough surface from what the question said. The object is resting on a rough surface. So remember, whenever an object is in contact with a surface, we are bound to have a normal reaction. So this normal reaction is vertical to the point of occurrence. So we have a normal reaction, which is at 90 degrees to the point of occurrence. And again, since this object is moving to the right, it means we are going to be having a frictional force which opposes that motion. So we have a frictional force to the left. Call this frictional force F. Now, due to this spring providing restriction to this object, total distance traveled by the spring is going to be what? Maximum compression, which is 40 millimeter plus what? 600 millimeter, sorry. So 40 millimeter plus 600 millimeter becomes total distance traveled by the spring to provide restriction to this object. Now, we need to find what then is the work done by the spring and the work done by this object. So total work done now is simply work done by the object and work done by the spring. So let's start with the object. How do we find work done by the object? You know that work done is simply force times distance, but the force in this case now is what? A frictional force. The force in this case is simply a frictional force. So therefore, the work done by this object is work against what? Friction. And that work done is going to be equal to, okay, work done by object. Okay, now from the equation, from the principle, u1 to 2, u1 to 2 is simply work done against friction, so use wf to indicate that, plus total work done by what? Spring. Okay, so this is work done by friction, this is work done by spring. That becomes our total work done. Then how do we find work done by friction? Once again, let's draw a free body diagram of the object of mass. So this is the object of mass, and every object of mass, every object that possesses a mass has a weight which acts vertically downwards, and the weight is simply mass times what? Gravity. Again, this object is resting on a rough surface, so we have a normal reaction called that N. Similarly, we have a frictional force. Since this object is moving to the right with a speed v equals 2.5 meters per second, it means we have a frictional force that opposes that motion. Call this frictional force F. So the work done by friction is simply going to be, since we know that frictional force is always a negative force, we have minus frictional force multiplied by total distance it takes this object to get to the spring. And total distance it takes the object to get to the spring, let's pull this diagram back once more. Remember, it's going to be 600 millimeters plus what? 40 millimeters. So that gives us 640 millimeters. This becomes our total distance traveled, or total distance provided by this spring to restrict the motion of this object. So 40 millimeter plus 600 millimeter. Okay. Alright, so now what then is frictional force? Remember, frictional force is given as mu n. F is always taken as mu, where mu is the kinetic friction, friction coefficient multiplied by n is a normal reaction. So if you put that into this equation, frictional work done becomes minus, in place of F, mu k, which is the coefficient of kinetic friction, times normal reaction times total distance, and our total distance is 640 millimeter. Okay, how do we get our normal reaction? Look at the diagram. From equilibrium law, summation of vertical force is equal to 0, upward force positive, downward force negative. And if we look at this beam or this structure or the package, our normal reaction is pointing vertically upward, so it's taken as positive. Then we have the weight of the object acting vertically downwards, minus W, and this is equal to 0. So this simply means that our normal reaction is equal to weight. If we send weight over here, and you know what weight is? Mass times acceleration due to gravity. So this implies that normal reaction is equal to our mass. Mass is 60 times acceleration is 9.81, which implies normal reaction is equal to, let's obtain that product. 60 multiplies 9.81. That gives us 588.6 Newton. So this is our normal reaction. So if you obtain this to be your normal reaction, then let's plug into the equation for the frictional work. This implies that work done against friction is equal to minus 588.6 multiplied by mu k times total distance x. Remember, I explained earlier is 640 millimeter, which is 0.64, which is 640 divides 1000. That gives us 0.64. So this implies that the work done against friction is equal to, let's obtain this times 0.64. We have it to be 376.704. So minus 376.704 mu k. So you keep this. Next, we need to find the work done by the spring. Okay. So we'll find the work done due to friction. Now let's find the work done by the spring. Not forgetting we were given two compression for the spring. The first compression was given simply as which is our initial compression was given simply as 120 millimeter, which is 0.12 meters. Final compression, we have an additional deflection of 40 millimeters, so 120 plus 40 would give us 160 millimeter, and we had this to be 0.16 a meter. So it means that we are going to be looking for the work done for each of these compression, first compression and second compression, then we sum them all up together. Now, keeping that in mind, recall that work done by a spring is stored in the spring as potential energy. The work done by a spring is stored in the spring as potential energy, and it is given simply as 1 all over 2 times the spring force times the deflection. Okay, in this case, it's going to be maximum deflection times maximum deflection. Work done in the spring is always stored as potential energy, and it is given as half times the spring force times maximum deflection. So we are going to be looking for the first spring force, second spring force, then use this particular equation to find work done in the spring. Okay. So work done by spring is going to be equal to 1 all over 2. Work done in the spring is stored as potential energy. Okay. And it's simply given as 1 all over 2 times the spring force or the first spring force times maximum deflection x. Okay. Plus again 1 all over 2 times the second spring force F2 times maximum deflection change in x. So this is simply going to be equal to, of course, 1 over 2 is common. So you have 1 all over 2 times deflection is also common, maximum deflection is common, into spring force 1 plus spring force 2. So let's find what are now the spring forces. Spring force 1, spring force F1 is simply taken as K multiplied by X1, where K is the spring constant. So this is equal to, spring constant was given as 20 by 10 to the power of 3, which is 20 kilonewtons per meter. Okay, so 20 multiplies our first compression. Remember, since it is compression, it's now going to be what? Negative. So the first compression was given to us as 120 millimeter. X1 was simply given as 120 millimeter, which we converted to be 0.12 meters. Now, since this is compression, then it means we are going to be appending negative for compression. Similarly, for the X2, also negative for compression. So if we plug that into this equation, you're going to simply have the first spring force to be 20 times minus 0.12 in meters. Negative because it is compression and not expansion. So let's find this product then. So F1 is equal to, that gives us minus 2400 Newton. So this is our first spring force. Now, second spring force, F2 is going to be equal to still K times X2. Now, K remains 20 by 10 to the power of 3 multiplies X2 is the final compression, and the final compression X2 was given to us as 0.16. Now it's going to be what? Negative, since it is compression. Okay. So we have times minus 0.16. So this simply implies that F2 is equal to, that gives us minus 3,200 in Newton. So this is our second or final compression. So if you take a look at the equation we stated earlier, we said that the work done by a spring is stored as potential energy, and the potential energy is simply what? Half F1 times maximum deflection plus half F2 times maximum deflection, which we said half is common, maximum deflection is common, and we have this. So all we need to do is add F1 and F2, multiply 1 all over 2 times maximum deflection. But not forgetting, in the question, maximum deflection was given as 40 millimeter. Okay, from the question, maximum deflection was given as 40 millimeter. So okay, so our spring work, therefore the spring work is equal to, we said, half times maximum deflection multiplies F1 plus F2. So this is equal to half times maximum deflection was given as 40 millimeter, which is 0.04 in meters, multiply F1. We obtain F1 here as minus 2,400, and we obtain F2 here as minus 3,200. So if we multiply everything, we are going to be having the spring work to be equal to, so we have the spring work to be equal to minus 112 in joules. So recall, we said that total work done U1 to 2 is equal to the frictional work done, okay, WF, plus the spring work done, WS, and this is equal to, not forgetting our frictional work done, we obtain minus 376.72 minus 376.704 mil K. So we plug it into that equation. Alright, so in place of this we have minus 372.704 mil K minus, for the spring work done we have 112, so minus 112. Alright, so this implies U1 to 2 is equal to, okay, minus 372.704 mil K minus 112. Alright, so this is now our work done. So recalling the principle of work and energy, okay, recall, from the principle of work and energy, T2 is equal to T1 plus U1 to 2. But T2 is the final kinetic energy, which we obtained earlier as 0. Okay, so we had T2 to be 0. So 0 is equal to, then we obtain T1, and we obtain T1 to be 187.5 joules. So let's plug it back into the equation. So for T1 we had 187.5 joules. For U1 to 2 we had minus 372.704 mil K minus 112. Okay, so this implies 0 is equal to, let's evaluate, 187.5 minus 112. Okay, that gives us 75.5 minus 372.704 mil K. Now let's send minus 372.704 mil K over to this side. Negative sign cross an equal to sign becomes positive. So we simply have 372.704 mil K to be equal to 75.5. Alright, now we make the coefficient of kinetic friction subject of the formula. This simply implies mu K is equal to 75.5 all over 372.704. So this simply implies that our coefficient of kinetic friction is equal to, we have the value to be 0.20, and that is the answer of that given question. Alright guys, so that's how you apply the principle of work and energy to tackle problems in kinetics of rigid body. I will see you in the next video with more questions. Thanks and cheers.